We are given two quantities. Quantity A is 65 to the power 40 and quantity B is 255 to the power 30. And we are asked to find the relationship between quantity A and quantity B. And the options given are quantity A is greater, quantity B is greater, the two quantities are equal, and the last option is the relationship cannot be determined from the information given. And this is a very typical format of quantitative comparison questions that are often asked in standardized tests like GRE. And in this particular problem, we are dealing with exponents. So we have 65 to the power 40 on one side and 255 to the power 30 on the other. And the difficulty here is, just by looking at these two quantities, it's not possible to immediately infer which of the quantities may be greater. Because in quantity A, we have a smaller base but a larger exponent. And in quantity B, we have a larger base but a smaller exponent. So by base and exponent, what I mean is, if you look at 255 to the power 30, base is 255 and the exponent is 30. So the common strategy for dealing with these problems is basically to reduce, either the expressions to a common base or the quantities to a common base. For example, a to the power b, a to the power c, where a is the common base, and now all you got to do is compare the exponents b and c. The other strategy for this might be to actually go for a common exponent. If you can somehow bring the exponents to a common value, for example, b to the power a, c to the power a, then all you need to do is compare the bases now. So both of these strategies work, but how do we go about, which strategy do we apply, really depends on the particular problem. Now, here we start first of all by taking a look at the bases and seeing whether we can break down the bases. So 65 can be broken down as 13 multiplied by 5. And the reason we're breaking down the bases to see if we can, spot some commonality that might, give us a clue on how to bring some degree of parity. Because 65 and 255 and 40, 30, they all look very, very different, right? So 65 can be broken down as 13 multiplied by 5, and similarly you can break down 255 as 51 multiplied by 5, and 51 can be further broken down as 17 multiplied by 3. So these are the prime factors of 65 and 255, and other than the common factor of 5, nothing else looks that much common or similar between the two. They're still two different quantities with very different constituent prime factors, besides the common factor of 5. And the other thing to note is, both of these numbers, 65 and 255, are not perfect squares or cubes or so on. So the thought of manipulating their exponents is kind of, there's less chance of getting something there because they're not perfect squares or perfect cubes. Now, one idea that came to my mind when I was solving this was, can we take a logarithm of both sides and then try to see what we can come up with? But log tables are not usually supplied in standardized tests like GRE and so that may not be an option in this case. And usually these problems, they have a simpler way to deal with, provided that you can spot what's the correct way. So when we have a situation like this, the numbers themselves are not, that convenient, one thing to think about is, really look for numbers in the neighborhood of the numbers that are given, which might be, better from the standpoint of either they're multiples of 10 or maybe they're, perfect squares or perfect cubes. They're just easier to deal with. And if you think about what numbers are around 65, one such number that immediately comes to mind that's actually very close to 65 is 64. And we know 64 is a perfect square because it's 8 square, but it's also a perfect cube. So 64 is basically 4 cube. So we have 65 greater than 4 cube. Similarly, when you think about what numbers are around 255, the number that's very convenient from the standpoint of being a perfect square is 256. So 255 is less than 256, and 256 is basically 4 to the power 4. So here, by just looking around the numbers 65 and 255, we have suddenly found, a common base, right? It's still an inequality. It's not an equality, right? It's an inequality, but at least now we have a common base 4. Now, we want to get the quantities A and B on, either sides of those two inequalities. So let's start with quantity A. If we raise this inequality to the power 40, then the inequality is still preserved, right? So we have 65 to the power 40 is greater than 4 cube raised to the power 40. And the right hand side, basically the exponents on the right hand side of this inequality will get multiplied. So it will become 65 to the power 40 would be greater than 4 to the power 120. And we do the same thing for the other inequality. We bring quantity B by raising both sides of the inequality to the power 30. So we have 255 to the power 30 less than 4 to the power 4 whole raised to the power 30. And this will become 255 to the power 30 less than 4 to the power 120. So from these two inequalities, so we have 65 to the power 40 greater than 4 to the power 120, and 255 to the power 30 is less than the same quantity, 4 to the power 120. So from these two inequalities, it's pretty logical to derive that 65 to the power 40 would be greater than 255 to the power 30. So the correct option in this case would be option A, quantity A is greater.